So we saw that the orbit has six fixed elements, which are the semi-major axis, the eccentricity, the inclination, the argument of perihelion, and the longitude of the ascending node, and the true anomaly. The six quantities specify the orbit, and of these, only the true anomaly is changing. All the other ones are constant. So even if there is a perturbing force that acts on the system, any instantaneous set of position and velocity vectors always defines a set of six orbital elements. Now imagine what happens if you have an orbit and you are slightly perturbing it. The question is, how are these quantities going to change? So for that, we can consider a small disturbing force where RT and N are the magnitudes of the radial, tangential, and normal components of the force, respectively, and R hat, theta hat, and Z hat are the standard unit vectors in cylindrical coordinates. So based on that, let's find out what are the expressions for A dot, E dot, I dot, omega dot, and big omega dot. For the semi-major axis, we realize that the energy being minus mu over 2a, so we can take the derivative of this to find the expression for A dot. Now we can also equate the change in energy with the work done by the force dF. So this is equal to R dot big R plus R theta dot big T. Now to write the velocity in useful terms, we need to go back to the equation of the orbit. And if we take the derivative of this, we find since f is the only quantity that is changing, and we equate theta dot with f dot, since theta is equal to f, and using the definition of the angular momentum, we can substitute the rf dot in the equation for the r dot. So the r dot is equal to na over square root of 1 minus z squared times z sine f. And similarly, rf dot is equal to na over square root of 1 minus z squared, 1 plus e cosine f. So if we put these definitions onto the equation for the variation of the energy, then we find the expression for A dot. Now, because the mean motion depends on the semi-major axis, now substituting this value for the mean motion into the dAdt equation. Oh, and we forgot here the mu over 2a squared in the upper equation relating A dot and R dot R plus R theta dot T. Reinstating that, so we can see from this equation that only forces in the plane of the orbit can change the semi-major axis. Okay, let's look at the angular momentum. The rate of angular momentum change is equal to the applied torque. So given the expression for the perturbing force, this is equal to RTZ minus Rn theta. Since the Rn theta component, the azimuthal component, can change the direction of the angular momentum vector, but not its magnitude, we concluded that the magnitude is only changed by the z component. So it's only azimuthal forces that can change the angular momentum. Now let's look at the eccentricity. For the eccentricity, it is equal to the square root of 1 plus twice the angular momentum squared times the energy over mu squared. So taking the derivative of this, we already have the expressions for L dot and E dot. Now if you use the equation on the orbit, the expression for the angular momentum, and the equation we already found for the evolution of the semi-major axis, and this expression implies that the eccentricity can only be changed by the application of forces in the orbital plane. For inclination, we realize that the z component of the angular momentum is angular momentum times cosine of the inclination. And if you take the derivative of this equation, I'll save the algebra and only quote the result. So since the IDT, the derivative of the inclination, depends only on n, the vertical component, we concluded that only forces normal to the orbital plane can change the inclination. we have this set of equations then for the derivatives of the orbital element for the longitudinal descending node and the argument of perihelion. Similar expressions can be found. I'm just going to quote the result again. The angular momentum is not an orbital element, but let's keep this because the angular momentum, the derivative of the angular momentum, is a quantity of physical importance.